Okay, so in this module, we're going to talk about the components of the different optical instrument, or the one that is used in spectroscopy. Okay, so in our previous discussion on module 4.1, we said that the components of the optical instruments are usually made up of 5 parts or 5 components. So we have here the light source, okay, or the source of radiant energy, uh, the sample holder, which we could say is a transparent container for holding the sample, and then a device that isolates a restricted region of the spectrum for measurements, or what we call the monochromator, and then the detector, so the radiation detector, which converts your radiant energy to a usable electrical signal. And for you to be able to interpret this signal, you have this so-called signal processor and readout, okay, which displays the transduced signal on the meter scale, a computer screen, and a digital meter or other recording device. So usually 1, 4, and 5 are arranged in the same way for most of the types of the measurement. So the one that can change would be 2 and 3. Okay, the way you can do it in some, the monochromator comes first, in the others, the monochromator comes after the sample holder. So if you're going to look at the block diagram of the different optical instruments, so you could see those 5. So here in the absorption, you have 1, 2, 3, 4, 5. In fluorescence and phosphorescence, so you have here the source, then the wavelength selector, and then the sample, and then you have again the wavelength selector, the detector, and the signal processor. You will know why it is like that when we go on molecular luminescence. And then in emission or chemiluminescence, so you have here a sample, and then you have the source, the wavelength selector, then the detector, and the signal processor, and the readout system. Okay, so if we're going to look at the figure from the previous slide, so you will see that 1, 4, and 5 are usually the same all throughout the different spectroscopic methods. So the configurations for your absorption, fluorescence, and phosphorescence require a radiation source, whereas the emission and chemiluminescence do not. And the sample holder, we could say, is integrated in the optical path either before or after the wavelength selector. So in some configurations, additional wavelength selectors are integrated. So hence, these components are designed into a framework appropriate for the type of chemical analysis. Okay, so if you're going to look at the layout that we have for a spectrophotometer, so it refers to the specific arrangement of the components of the instrument in terms of the path of light. Okay, so everyone has the light source, so that's the one that you usually follow. And there are usually 2 common optical layout. So one that is the single beam optical layout, wherein there's just it is just provided a single path to the cell holder from the light source. So we could say it's just linear, straight. Okay, so that's what we call the single beam optical system. Okay, now the other layout is what we call a double beam optical system. So if you have a double beam optical system, it provides a reference and a sample path for the light source. And the way that you do it is for correction purposes, used to correct for the non-analyte absorption signals. So what are these? The reflected or stray light, the analyte in the reagents, and the absorption by the reagent. And if you're going to look at the block diagram of a double beam spectrometer, these are usually separated by space. Okay, so you have here the light source, the wavelength selector or the monochromator. So it passed through here. There's a splitting of the radiation beam into two beams, okay? So one would go to the referencer and one would go to the sample cell. And then in these instances, since they're separate path of your light or radiation source, difference in the what we call the radiation. So you will also have two detectors, one that will monitor the signal from the referencer and one that will monitor the one coming from the sample cell. And then, okay, it will have a difference amplifier until it is transmitted to your readout system. Okay, so if you're going to look further, the double beam spectrophotometer, this time separated by time, like the one that we have here. So you have here a light source, monochromator or filter, and what you have here is some sort of chopper, a beam chopper. So the radiation is alternately sent to the reference and the sample cell. So it's just like going to the reference cell and then going to the what we call sample cell. Okay, and when that happens, okay, you're going to have what we call another beam that will connect the signal that you get from the sample cells and mix it with the one coming from the reference cell. And then it will be detected by one detector, okay? And then amplified for you to be able to read in the readout system, okay? Now, the advantages of this double beam spectrometer separated by time is you can have a wavelength scanning, okay? And the good thing at this is if you have a very good detector like a photomultiplier, PMT, okay? There's only what we call little trip. Now, the advantage of this one, since you're going to able to scan the wavelength at different wavelength, is the so-called cost. So since it has a more advanced feature, it is going to be more expensive. It's a little bit what we call complex. Okay. And this is the one that is commonly used as of this present in most of the spectrophotometer. Now, if we're going to look at the optical layout this time with the so-called AAS, so you can also have a single beam and a double beam. So if you're going to look at the block diagram that you have here, so your sample is introduced in such a way that it is converted into an atomizer, or we could say a nebulizer. You will know about that when we go in the AAS. And then there's a light source. Okay, so light source, usually this is just a flame. It will burn the thing. And then there's a monochromator. So it select the wavelength for you to monitor a certain, let's say, metal, and then a detector, and then a readout system. Now, if you have a double beam, okay, so you have the sample and the atomizer, the same thing there, they will come after the light source. But after the light source there, what happened, the one that passes to the atomizer is going to be mixed with the one that passed to the reference beam. And then the monochromator, okay, and detected by the detector, and then obtained by the readout system. Okay, so the one that you have, the so-called mechanical beam chopper in double beam spectrometer, usually it looks like this. So the rotating disc would block the transmission of the light. So that means the percent transmittance would be 0. And it's putting a mirror on the face of the rotating disc will redirect the light to an alternate path. So I told you, okay, sample reference. So once it passes through here, it goes to the sample. Once it goes this here, it goes to the other way. Or let's say it goes here and then chop it. Okay, so this then so it's just like there's an alternating thing that happen. Now let's go on the first component in this optical instrument. So the one that we have there is the so-called light source. As I have told you before, this is the spectroscopic methods are only possible if there's a light, because spectroscopy is just looking at the interaction of matter with light. Okay, so what you need is a light source, is a stable radiation or a light source that's generate a beam of sufficient radiant power. It's needed for spectrometric analysis. And there's usually two types of these light sources. It can be continuum or a line source. So when you have a continuum sources, it emits a range of photons that changes in intensity over a wavelength range. So we could say this is the broadband. It's a wide range, or we could say a range of wavelength. Now, line source, on the other hand, is emit only a limited number of band or discrete line, and it only spans at a limited range. So if we're going to look at the light source, okay, as I've told before, a stable source of radiant energy. Now, if you're going to look at the property of this light source, okay, so these are here. It should be able to create the intended wavelength. Okay, so the light source that you have should meet the wavelength that is needed for a particular sample. It must be stable, so there should be a constant transmitted radiant power with good precision. You don't want it to be fluctuating while you're doing the analysis. And in addition to that, it must be intense, highly intense, or have high intensity. It has high radiant power, which allow absorbance to be easily detected. Okay. One common example of the light source that we usually use in most spectrophotometer is the so-called hollow cathode lamp. Okay. So if you're going to look at the examples here of the light source, line source, so it's a discontinuous and what we call discrete. So this is an example of this so-called hollow cathode lamp. And usually, this hollow cathode lamp that we have there is a multi-element for better UV light transmission with embedded quartz window. Now, another light source that we can also look on is the so-called laser, which is just light amplification by stimulated emission of radiation. So laser is a good light source here. But unlike, let's say, the hollow cathode lamp, the range covered by laser is a little bit specific, or more narrow. Okay. So if we're going to look at the light source, as I have mentioned, it could be continuum or a line. So if you're going to look at the spectrum of a continuum source, it is much broader than a line source here. So as you could see here, there's a range wherein the light source, the continuum light source, can provide the radiant power that you need compared to the one which is a light source like this one. So you can just use it at this wavelength, and this wavelength. So whatever the wavelength that you have here, here, and here. Okay. So as what I said, a continuum source, this provides a broad distribution of wavelengths within a particular spectral range. A line source, on the other hand, it emits a limited number of narrow spectral lines. And if we're going to look at some of the specific example of continuum source or the continuous source, this is the one that we have. Now, Mamigo mentioned to you about xenon, the tungsten lamp and the deuterium lamp. Okay, so this is the wavelength region that they cover. Okay, now if you're going to look at this, the deuterium lamp is used usually for the UV molecular absorption. Now the tungsten lamp would be used in the UV visible IR region. So if you're going to look at this, the tungsten lamp can only cover until 240. So as what Mamigo told us in our last meeting, there's usually a shift in the light source once you get a certain wavelength. Okay. Now, if you're going to use molecular fluorescence, xenon arc lamp is the what we call common light source. Okay. You can also have other light source here depending on the type of spectroscopy that you use. So if you use a visible near IR, usually you have a tungsten lamp. Okay. In the IR, you can have Nernst glower, nichrome wire, or the so-called glow bar. So if we're going to go specifically on this light source, so this is what the tungsten lamp look like. So it provides the light source if you're measuring between 400 to 1200 nanometers. So that's a visible spectrum. But most analysis also covers the so-called UV region. So in that case, this is provided by the deuterium lamp, which is between 190 to 400. So in most spectrometer, you have these two light source if you analyze this UV visible region. Now, in terms of the tungsten filament lamp, this is the light source that provides to from visible to near IR. So near IR, usually they call it NIR. Okay, it's around 400 to 1200 nanometer, or from 350 to 2500 nanometer. It's a continuous source like your tungsten and deuterium lamp. Okay, it's a broad range of frequencies, and it is based on Max Planck black body radiation, wherein the heated solid filament glows. Light emitted will be characteristic of the nature of solid filament, but more so on temperature. Okay. Now, further discussion of the so-called deuterium and the hydrogen lamp. So this is the one that provides the UV region. It is a continuous source. Okay, a broad range of frequencies. Energy is of we could say based on the electric excitation of your hydrogen or deuterium at low pressure. So you know deuterium is just an isotope of your hydrogen. So what happened here in the presence of the arc lamp, some of the energy, electrical energy, is absorbed by the deuterium, or in some cases the hydrogen, which results in the deassociation of the gas and the release of the light. So you have here deuterium and then energy. Okay, you excite the electron. Okay, and what happened there is there's a source of light that comes out of this. But and if you're going to look at the intensity of the light, okay, or the power that you have there, it decreases as the wavelength becomes longer. Okay, so light will vary continuously from 160 to 375 nanometer due to the different frequencies going into D prime 2 and D double prime. And if you're going to look at the lamp, it's made up of quartz, since glass absorbs light at more than 350 nanometer. And I think this is also related to the cuvettes that you're going to use, the material that you use. Why glass cannot be used for UV analysis. Okay. Now, the hollow cathode lamp On the other hand, it's filled with an inert gas, so it's maybe a neon or an argon at low vacuum, only 1 to 5 torr. Now, the hollow cathode is made up of the metal having the desired spectrum. You have where an exit window composed of pyrex and quartz, depending on the wavelength that is produced. So the lamps receive an applied potential of 300 volts direct current. Okay, so if we look at the mechanism on how the hollow cathode lamp works, so what happened there? There's inert gas that is ionized at the anode to high potential, which is 300 volts. Now, these ionized gas are attracted toward the cathode. Okay, so the fast-moving ions strike the surface of the cathode and physically dislodge some of the deposited metal atoms and dislodge into gas phase. So in the process called sputtering. Okay, so if you're going to look what is happening here, I think this illustration is best shown here. Okay, so those are the steps that is happening. So the inert gas is ionized, so you apply high potential, forcing the inert gas to be ionized. And then what happened to the ionized gas? They are attracted towards the cathode. Now, the fast-moving ions strike the surface. So it strike the surface there. It's going to dislodge some of the metal atoms, like that one. So it discharges the surface there. So some of the metal are what we call dislodged or sputtered. The sputtering, of course. And then as you go on, the displaced atoms are excited by the collision with the electron. And the excited elements relaxes to ground state, emitting the characteristic atomic emission spectrum of the metal. Okay, so the way that you could look at this one is your metals or the atoms that you have there are excited by the collision with the electrons. And once they go to the excited state, they go to the ground state, and that's where they emit, okay, energy. Now, the advantage of this hollow cathode lamp, it has a sharp lines specific for elements of interest. The disadvantage, again, has something to do with the cost. Okay, why? Because each element you use different lamp. Now, you can watch the video here to show how your cathode lamp are attached or detached to the instrument. I'll try to video how we use or replace the hollow cathode lamp in AAS maybe next week, because we have an experiment on AAS, okay, so that you can see it firsthand. Now, we can also have this electrode-less discharge lamp. Now, this electrode-less discharge lamp, we could say, is a sources of the atomic line spectra. And it's available commercially for 15 or more elements. It exhibits the better detection limits for some elements like selenium, arsenic, and antimony than those hollow cathode lamps. So the typical lamp is constructed from a sealed quartz tube containing a few torr of inert gas such as argon and a small quantity of the metal or its salts whose spectrum is of interest. Okay, now the mechanism of this electrode-less discharge lamp is the lamp is energized by an intense field of radio frequency or microwave radiation. So the argon ionization would result to ions that are accelerated by the high frequency component of the field until they gain sufficient energy to excite the atoms of the metal whose spectrum you sought. Okay. So those are the lamps. So the next one that we have is laser. So laser amplification by stimulated emission radiation. I have experience using laser before. I still have some access to this laser source that we have. So what is the main properties of laser? It's, we could say, monochromatic. So I use laser at 488 nanometer line, 550 line, and 775 line. Those are the line source that I have in what we call Raman. But I also use some high-powered lasers, okay, that when we double or triple frequency will become a much longer wavelength, from shorter wavelength to longer wavelength. Extremely bright. It has a high power at one wavelength. It's collimated or has a parallel rays. Okay, so the way that you have this what we call thing is collimated, and most of them are polarized. So that means the electric field oscillates on one plane, and coherent. All waves is also in one plane. Now, if you're going to look at the basic principle of lasing, okay, it has something to do with population inversion. Okay, so if you're going to look at the mechanism here, so the electron is pumped to a higher energy level. Now, the pumping level is usually unstable, so the electron quickly jumps to a slightly lower energy. And when that happens, the electron relaxes to a lower energy state and releases a photon. Okay? You really remember, if you go to an excited state and then you go back to a lower state, usually the higher energy states, they're unstable. Okay, so when they go back to a lower energy state or state of lower energy level, there are some radiation or energy that is released. So what happened? When it releases a photon, the light and an electron in an excited state energy level produces two photons of the same wavelength and phase. And with the mirror, it reflects this what we call photon. So in this population inversion, there's a higher energy levels must be more populated than the lower levels in order for lasing to occur. So if you're going to look at this mechanism, we could say there's pumping, spontaneous emission, stimulated emission, and absorption. We're going to discuss it in the next slide. So when we have this pumping, this is where an active species of a laser is excited by means of an electrical discharge, passage of an electrical current, or exposure to an intense radiation source. In a molecular level, several of the higher electronic vibrational energy level of the active species are populated. Okay. Now, the spontaneous emission, this is where the instance when there is emission that occurs and the path of the resulting photon vary from the excited molecule to excited molecule. So the fluorescence radiation produced by one of the species differs in the direction and the phase from that produced by the second species. And this usually yields to incoherent monochromatic radiation. Now, when you have a stimulated emission, the excited laser species are struck by photons that have largely the same energies as the photon produced by spontaneous emission. So it causes the excited species to relax immediately to the lower energy state and to simultaneously emit a photon of exactly the same energy as the photon that stimulated the process. Now, absorption would compete with the stimulated emission. So what happened here, there's two photons with exactly equal energies that are absorbed to produce the metastable excited state, which is identical to that attained by pumping. So if you're going to look at the schematic representation here of the laser, okay, so you have the active lasing medium. So what happened there? There's a power supply. So this is the pumping source, and then this is the radiation. So you have the mirror, okay, and that's the mirror that will just reflect back and then do it as the what we call the source of your laser. So there's a partially transmitting mirror. So everything that is produced there okay, it will come out as a laser beam. And I think it's best for you to watch this clip to determine how lasers are what we call produce. Okay. Now, to summarize the light source that we have, so if we have a continuous source from the vacuum, UV, visible near IR, and phi RR. So you have here the argon lamp and then the xenon lamp. So argon lamp is the one that you have in vacuum. Now, xenon lamp who covered some vacuum, most of the UV and the visible region, okay, and some near IR. Now, the hydrogen or deuterium lamp, it covers only the UV region. So you also have the tungsten lamp that covered some of the UV region until the IR region. And then the Nernst lower, the nichrome wire, and the global that covers the IR. Now, if you have a line, either you have the hollow cathode lamp or the lasers. So they covered, okay, a wide range from UV to near IR. So that's, we could say, the summary of the light source that we have. Okay. So the next item that we have is the sample holder. So this is where you going to put your sample or you introduce the sample in the system. Okay. So a sample holder or compartment is incorporated into the optimal instrument either before or after the wavelength selector, depending upon the design of the instrument. Now, the optical material used for sample cells varies depending on the radiation required in the given analysis. Now, in most of them, usually you have a transparent container for holding the sample. And among the desired properties a sample cell holder needs to have is fixed geometry. That's a constant path length. We all know all 1 centimeter, but as I've told you, you can have lower or higher than 1 centimeter, longer or shorter than 1 centimeter. Another property is transmit, okay, the wavelength of interest. So it passed through a wavelength of interest of high radiant power. You should be able to transmit it. Third, you hold the sample without chemical interaction. So whatever the composition of the sample, when you put it in the sample holder, it's just the same. If ever there will be an interaction, it is because it interacts with the light source, not with the container or with the sample holder itself. Okay. And for many purpose use, it should be easy to clean for reuse. Okay. So if we're going to look at some of the sample holder, so we have here the cuvette. So what do you need to remember about the cuvette? Maybe the composition. In UVBs, you use quartz. If it's around 300 to 900, you can use glass. But if it's around 400 to 700, you can even use plastic cuvette. Okay. You cannot use plastic if you're going to monitor at lower region or especially the UV region. Now, for the IR one, you're going to use this what we call the NaCl and the KBr cell window. But usually, if you're going to use this one, make sure you don't use water-based sample. Why? Because it's soluble in NaCl and KBr. They will dissolve some of this. So you can use the silver chloride. That's the one that I usually use as a cell window. Okay. So this is how this what we call container looks like, the sample cell holder. Now, if you're going to look at the configuration, the sample holder can be constructed to transmit light absorbed at 180 degrees to the incident light or allow emitted light to exit at 90 degrees from the incident light. Now, if you're doing absorption and emission, okay, usually the way that you have here, you have this cubit and then you just pass it through. But if you have fluorescence, so the way that you're going to do it, you're going to have the light this way, and then you're going to observe it 90 degrees Celsius, like me facing my hand. So this is the cubit, this is the light source. So I want to monitor it like this one, okay? It can contain gases at lower concentration. And as I've told you, you can have long path lengths. 1 centimeter and 10 centimeter cells are usually the more common one. Okay. Now, if you're going to use the optical characteristics of the components that we have here, so lithium fluoride will cover a wide range. And then the quartz or the fused silica, okay? And then the glass, the silicate glass, NaCl, KBr, and then you have the titanium bromide and titanium iodide and the zinc selenide. But the one that is common, I would say, is just the quartz. Quartz is more expensive than glass. So you can look at the link here to access the exercise by Cengage. Okay. So that is all about the sample holder. Okay, so let's continue. Now let's go now to the monochromator or the wavelength selector. So this is a device that isolates a restricted region of the spectrum for measurement. Okay, it separates the desired frequencies or wavelength from the polychromatic light. So the desired properties of this will be the narrow band pass. It selects your desired wavelength. And as much as possible, you want a large light throughput, resulting in a high radiant power for this one. So if you have a wavelength selector, so the nominal wavelength that you have there, that's the wavelength which our wavelength selector is set to pass. Okay, so if you have a nominal wavelength here, so this is the particular wavelength that you like. Okay, so the percent transmittance that you have there, it goes, it increases there, and then until it goes down. Okay, so the effective bandwidth that we want is just the width of the band of the radiation passing through a wavelength selector measured at the half the band's weight. So that's, we could say, the effective bandwidth here. Okay, and it's usually an inverse measure of the quality of the device. Now, if you're going to look at some of the wavelength detector, it can be of several types. You can have an optical filters. Okay, so this is just an interference of the Fabry-Ferro filters. You can also have an interference wedges here, okay, and absorption filters. We're going to discuss this as we go on. Now, we can also have the type of that monochromators. So this is in the form of grating and prism, okay, or you can have what we call an interferometer. So if you're going to look at these optical filters, one of the type that we have there is the so-called interference filter, or known as the Fabry-Ferro filter. The band selection in the ultraviolet, visible light, and in infrared region. So you have your band pass that's range from 1 to 20 nanometer. So the way that this interference filter would work, so you have a white light. As it passes through the different component there, glass, metal, dielectric, metal, and then glass, okay? It narrows the wavelength that you have. Okay, so usually this is made up of thin layers of metal and dielectric material, like calcium fluoride or magnesium fluoride. And it's coated on both sides, okay? With a film that is thin enough to transmit approximately half the radiation striking it and reflect the other half. So if it goes here, one would, half would be transmitted and the other half will be reflected. Okay. And if you're going to look at the relationship between the dielectric layer's thickness and the transmittant wavelength, this is what you have. So first you have n times the wavelength prime equals to 2d over cosine. Okay. And usually, this one is usually set to 0. And if that is the case, cosine 0 will be give you 1. So this is the expression that you have. So in air, you can have this expression where n is the order of the interference, the wavelength, lambda prime is the wavelength of the dielectric layer, d is the thickness of dielectric layer, lambda is the wavelength in air, and this n prime is the refractive index of the dielectric. Now, it is selected to absorb all but one of the reinforced bands transmission and is restricted to single order. Now, interference wage, on the other hand, this is a band selection only possible in the visible and near IR and IR regions. And it has a bandwidth of around 20 nanometer. So it consists of a mirrored, partially transparent plates separated by a wedge-shaped layer of dielectric material. So the dielectric has a different thickness and thus it can transmit a wide range of wavelength according to lambda equals to 2d n prime over n. Now absorption filters on the other hand, so this is band selection only in the visible region, and its materials to remove undesired wavelengths by absorbing them. So typically this is made up of what? A colored glass or dye suspended in the gelatin between the glass plate. This is less expensive than interference filters. It's just like your polarized glass. If you want to chop off some of the UV that comes into you. Okay, and if you have these absorption filters, they absorb a significant fraction of the desired radiation and may have a transmittance of 10% or less at their band peaks. So if you're going to look at an example here, so there's a green filter that you have here. So you have an absorption filter, and then you have this orange cut-off filter. So if you combine the two filters, this is what it has. So the cut-off filters that you have just have transmittance that's nearly 100%, but rapidly decrease to 0 transmittance over the remainder. So a narrow spectral band can be isolated by coupling a cut-off filter with a second filter. So those are what we call the filters that we use for wavelength selectors or optical filters. Now for the monochromators, these are designed for spectral scanning. And if you're going to look at this, there are still components within the monochromators. There's an entrance slit, a collimating lens or mirror. So if you have an entrance slit, it provides a rectangular optimal image. If it's a collimating lens or mirror, it produces a parallel beam of radiation. And then to disperse the radiation into its component wavelength, you have a prism or grating. Now the focusing element that you have there, it reforms the image of the entrance slits and focuses it on the plane surface, which is the focal plane. Now the exit slit, that's the one that isolates the desired spectral beam. Okay, so if you want to know how it looks like, this is how this monochromator looks like. So it's just based on the diffraction of the light. So this is the entrance slit. And then you have the collimating mirrors. Okay, so in the collimating, we produce a parallel beam of the radiation, and then it passes through this diffraction grating, and then that's where it has this focusing element, which is the mirror. And then by the time, okay, it goes out, it is already of a particular wavelength. So if you look at this, it consists of a series of closely spaced parallel groups cut or rolled into hard glass, metallic or ceramic surface with reflective coating, aluminum, gold, and platinum. So the UV and the visible regions, there's a 300 to 2,000 groups per millimeter. The IR region would have 10 to 200 groups per millimeter. Now, if we're going to look at the mechanism here of this grating, okay, if you have the echelate type reflection grating, it's based on the so-called Bragg's law, where N times the wavelength is equals to D times sine I plus sine R. So I is the incident angle, R is the reflection angle, N would be the order of the diffraction, your lambda is the wavelength of interest, and D is the spacing between the reflecting surfaces. So if you're going to look at this, this is what happened here. So there's your what we call I, the incident light, and this is the reflected angle, the incident angle and the reflected angle. And we're going to discuss synchronously how to solve problems like this one. Okay. So maybe you can go over this thing. Now, we can also have the type of monochromator that is prism. So when you have prism, what you usually have, when you have the white light pass through the prism, it will give you the rainbow color. So this is based on the refraction of light. So the different wavelengths have different values of refraction index, okay, in a given medium. And it has a higher index of refraction for short wavelength radiation than for long wavelength radiation. So prism monochromators is used to disperse UV, visible, and IR radiation. In the UV region, it's a quartz. In a visible and near IR, it could be material made up of glass. And the IR, that's what you have as NaCl and KBr. Okay. And if the grating monochromators is based on Bragg's law, the prism monochromator is based on Snell's law of refraction. Okay. So N1 is sine 1 equals to N2 sine theta 2. So if you're going to look at this one, the refraction of the light is passing from a less dense medium into a more dense where its velocity is lower. So this is the cornu and litho prism. So the cornu prism, there's a white light and then they will produce the different color. Now in the litho prism, there's a mirror, okay? And then you put the white light there and it is refracted to do the thing. So you're going to look at this like this, okay? Now, if you're going to look at the monochromator slit settings, okay? Usually when you decrease the slit width, it would result in a greater spectral resolution. So if you're going to look at the difference, you look at the 2 nanometer bandwidth. Okay, so all you see is just one. But if you're going to narrow or decrease the slit width, what do you see? You have a more sharper or a sharper, more sharp peak. And if you're going to decrease it further to 0.5, you could see that there are other peaks that you could see, which is not possible or which is not possible, or what you see is just a broad peak if you use a higher slit width. Okay, so how do you choose the slit width? As much as possible, you use the minimal slit. So this is when the resolution of narrow absorption is needed, or you can have a wider slit for quantitative work, where you have these spectral details. Now, if you're going to look at the wavelength selectors, okay, among the region that we have, so we could say from vacuum to UV, you have the fluoride prisms, and then from UV to near IR, you have the quartz prism, and then in the visible and the near IR, you can have the glass prism. Now in the IR, you can use the NaCl or the KBr prism. Now, if you use the grating, it will cover all the range that you have here. Interference plate, a little bit narrow, and also is interference filters, but much higher than interference plates. Now the glass filters is just, we could say, around the visible and near IR. Okay, so try to see if you can access the this self-test for you to understand more about the topic. And then we go with the part one, which is the detector. So a detector is a radiation transducer, and it's one that transforms the radiation energy that reaches the sample to an electrical signal. Okay. So two common types of radiation transducers are, we could say, the photon and the thermal detectors, and their sensitivity depends upon the wavelength. Now we have discussed about detector in our chromatography. Okay. So the principle that you have there is the same as the one here. In fact, one of the detector that is used there in chromatography is UVBs, the absorption at UV visible region. So the signal processor usually amplifies the signal from the transducer and some function mathematical operation. And the way that the radiation detector works is just converts radiant energy into usable electrical signal. Now, what are the desired properties? Stable. It should resulting in good precision. It should be sensitive to the wavelength of interest. You want it to have a high signal to noise or signal over noise ratio over a considerable range of wavelength. You want the response time to be fast. And a possible zero output signal in the absence of illumination, and the electrical signal that you have there is produced by directly proportional to the radiant power. Okay. And the common detectors that we can have here, okay, is the photon detector and the heat sensitive detector or thermal detector. So if you're going to look at the photon detectors, these are the type of detector that responds to the intensity of the electromagnetic radiation, striking them by changing a voltage or current emitted, okay, or required by themselves. And among these photon detectors are the phototubes, the PMT, photomultiplier tubes, the silicon photodiodes, and the photoconductive cells. And these are the wavelengths range that's recovered. Now, thermal detectors, on the other hand, responds to heat for IR detector. And among them that you have is the thermocouple, the bolometers, pneumatic cells, and the pyroelectric devices, and the wavelength range that you have seen from here. Now, if you're going to look at the phototube, okay, that's the first example of the photon detector. It converts the energy of an incoming photon into a current cell. And the conversion is done in a photoemissive surface known as the photoelectric effect. Okay, so if you're going to look at the mechanism that you have there when the photons above a minimum energy, if I'm going to make it bigger. So when the photons of the energy above a minimum, when photons above a minimum energy or short enough wavelength strike a photosensitive cathode, the electrons are ejected. That's the photoelectric effect. And then the electrons ejected from the metal cathodes are attracted to the anode. And then what happened? It caused an electric discharge or the electric current to flow and giving a reading on a meter. So the photons with the lower frequency, they do not have enough energy to remove the electrons. So the light with energy below the threshold does not eject electrons, and the current flow that they have is near zero. So no electrons are injected until the photons whose wavelength is short enough, when you say short enough, strong enough, or highly energetic enough to strike the photosensitive surface. And only the photons with greater energy than the minimum energy, the threshold of the energy, will eject the electron. So as I told you, this is the photoelectric effect that won Albert Einstein the Nobel Prize. Okay. Now we can also use the PMT, which is the most common one. So this is the photo multiplier tube. Okay. So you have here a sealed quartz tube filled with an inert gas at low vacuum. So the radiation enters the grill and strikes the photoemissive surface, converting it into a photoelectron. Now the photoelectron is attracted to a positive dynode, which produces a cascade of electrons. So it's just a cascade one. So when one is charged, the other, what we call electrons are what we call charged. So the energy is already finally collected at the anode, and a current pulse is recorded for each incident photon. So this is what is happening there. So you have here what? Dynodes. Okay, so if you're going to look at the radiation pass through here, okay, it's going to excite the electrons. And then several electrons will go produce a cascade effect, okay, through this photoelectron attracted to the dynodes. And they produce enough energy there, okay, to give you a current. I think the one that they use here is the CCD, the charge coupled divide. And then the PDA. So this is the photodiode array. So this is a semiconductor detector, okay, consisting of multiple individual diodes. So typically it's constructed from silicon or germanium, which is a semi-metal or metalloids. So the diodes are sensitive to the electromagnetic radiation in the visible and ultraviolet region of the spectrum. So this detector permits simultaneous measurement of multiple wavelengths and is more rapid than a dispersive instrument. So it can collect the signal from different wavelengths. And this is the one that is commonly used in spectrophotometer right now when you're doing a scan. Okay. So if we're going to summarize what we have in the detector. So typically the one that is used is the photon detectors, at least in the UV visible absorption spectroscopy. Now for the IR, you can have mostly the thermal. So the only one that is used in the IR is the photoconductor among photon detector. Okay. Now the last that we have in this module is the signal processor or the readout system. So the signal processor and the readout, this displays the transduced signal on a meter scale, a computer screen, a digital meter, or another recording device. So the way that you look at this is a signal processing. So there's an amplifier, okay? So what the signal processor do is amplify the signal coming from the detector and convert signal coming from the detector into a form that is easily displayed. So there's really a conversion from current to direct current voltage, and the form of the readout: computer display, digital or analog readout, strip chart recorder, or integrator. So usually right now it's all numbers. Before it's like you have to look at a certain line, at what number it is, or what we call connected. Okay. Yeah. Right now, let's say this, like this watch. Okay. So you see that's an analog one, but right now it just displays you right away the number or the reading. So we're almost done. And the last two slides that we have here is just some terms that you must be familiar with. So when you're talking about spectroscope, that's an optical instrument used for visual identification of atomic emission line. So we have one where we put it in the source and we try to look at the line spectrum. And then if we have a colorimeter, this is the human eye act as a detector for absorption measurement. And then we have a photometer. So it contains a filter, but there's no scanning function. And then if we have a fluorimeter, this is a photometer for fluorescence measurement. And if we have a spectrometer, it provides information about the intensity of the radiation as a function of wavelength or frequency. And lastly, if you have a spectrograph, this records simultaneously the entire spectrum of the dispersed radiation using plate or film. We don't usually do that. And the last that we could have here is the so-called spectrophotometers. So these are spectrometers that allow measurements of the ratio of the radiant powers to two beams, which is a requirement to measure the absorbance. It is a more sophisticated system of separating the light into the individual wavelengths and measuring the intensity at each individual wavelength. So typically, okay, if you have a spectrophotometer, you have a monochromator and a scanning instrument. So spectrophotometer is made up of two instruments, a spectrometer for producing the light of any selected color, okay, which is the wavelength, and a photometer for measuring the intensity of light. So the instruments are arranged so that liquid in a cuvette can be placed between a spectrometer, beam, and photometer. Now, other terms here, the incident radiant power, okay? So that's the radiant power in what's incident on sample. So incident intensity, that's the alternative symbol that you can have. And then the transmitted radiant power, which is P, that's the one that was transmitted by the sample. That's the transmitted intensity. And then you have absorbance, which is just equals to the log of incident radiant power over transmitted radiant power. Or alternatively, in most biology, they use it as optical density. In some, they use it as extinction. You can have the transmittance, which is just the transmitted radiant over the incident radiant power. Okay, it could be called transmission. You can have the path length of the sample, the length over which attenuation occurs. You can have absorptivity or molar absorptivity. Okay, so that ends this module.